My name is Seong Kook Lee from Seoul National University. Today's presentation is about the star formation status of high-redshift galaxy clusters. And this work is not done in the NEP fields, but in another multi-wavelength survey field, which is called as UK's UDS or SSDX field. And today's presentation is mainly based on these two published papers and some additional ongoing works. And this work has been done in collaboration with these researchers listed here. At local, if we see the galaxy properties, you can see a clear bimodality in many galaxy properties, such as colors, star formation rates, or their ages. One example is shown here. This figure shows the correlation between galaxy's mass and the 4,000 angstrom index in different environments, from fields to clusters. And here we can see a clear bimodality in the sense that in field regions, young galaxies are the dominant population, while in cluster region, majority of the galaxies are old ones. However, this clear bimodality becomes more complicated when you go to higher redshift. This figure shows the environmental dependence of median star formation range, studies done in Cosmos field, and at relatively low redshift, you can see that there still is a bimodality in a sense that star formation activity in dense environment is much lower than in the field regions. However, when you go up to the higher redshift, this environmental dependence weakens and it almost disappears up to redshift around 1. So we can think that some important changes occurs in star formation activities of galaxies in dense environment between redshift 1 and 0. And another thing you can see when you see the high redshift galaxy clusters is this. This figure shows the quiescent galaxy fraction of high redshift galaxy clusters at different redshift ranges. And you can here in this figure, these blue squares are the mean values of the field at corresponding redshift, and black symbols shows the quiescent galaxy fraction of individual galaxy clusters. And here we can see that some high-redshift galaxy clusters have a high level of quiescent galaxy fraction already, while other clusters have relatively low level of quiescent galaxy fraction. So this figure shows that high-redshift galaxy clusters show cluster by cluster variation in their star formation status. And naturally arising question would be what causes this kind of variation among galaxy clusters? So we decided to do the spectroscopic follow-up study of these high-redshift clusters found in the UDS field and using Magellan and IMAX instrument. And here in this figure, this red colored circles shows the primary targets of our follow-up. So these three are located at around redshift 0.9 and showing different level of quiescent galaxy fraction. And these three again shows different levels of quiescent galaxy fraction residing at similar redshift of 1.3. So we did follow-up, spectroscopic follow-up of these cluster candidates. And here is some basic settings of our observation. And one thing I want to say is the strength of the Magellan IMAX is a large field of view. So we can observe several clusters within a single mask. And from this middle figure shows the examples of some spectra of galaxies observed in this Magellan IMAX. And from this observation, we can measure the spectroscopic redshift of some galaxies And then from this, we can confirm 6 galaxy groups or clusters located at latitude 1.9 and 1 at latitude 1.3. And as I mentioned, the IMAX has very large field of view, so we can observe not only the galaxies within the cluster, but also the galaxies outside the clusters near galaxy clusters. And using this spectroscopic data combined with photometric redshift data, we analyze the large-scale structure of these clusters and surrounding regions. These two examples shows the galaxy clusters confirmed from our observation, and these two reside at very similar redshift, around 0.87, and but these two clusters shows very different level of quiescent galaxy fraction. With this one uh, has relatively low level of quiescent galaxy fraction, while this one has already 0.45, which is relatively high level of quiescent galaxy fraction. And comparing these two clusters, we can see that the around near this galaxy cluster, there is a overdense structure connected to this galaxy cluster in this case. And also we confirmed that this structure is at the same redshift as the cluster from our Magellan observation. Here, red symbols and blue squares are the galaxies with confirmed spectroscopic redshift from our Magellan observation, and these green triangles are the ones whose spectroscopic redshifts are from literature. And all of these are at the same redshift range. So we can see that these structures are actually at the same redshift and connected to this cluster. And from this analysis, we can see that there exists a trend or correlation between the extent of connected large-scale structure and clusters star formation status, in a sense that clusters, uh, which is more connected to the nearby large-scale structures, have relatively lower level of quiescent galaxy fraction. And to analyze this correlation in a more quantitative way, we divide the quantity called as FF fraction, and I will explain briefly about this. So this is the cluster centered region, and this red region shows the where the galaxy number density is higher than 2 sigma level, and also connected to this central cluster. We found this connection using friend of friend algorithm, so we called it as a FF fraction. And we did this analysis for galaxy clusters at 0.65 and zero point 0.8, and found this correlation between FF fraction and quiescent galaxy fraction. So uh, again, we confirm this correlation exists between the extent of connected large-scale structure and the quiescent galaxy fraction. And also from this figure, we can also see the relative evolution of this quiescent galaxy fraction, in the sense that for the clusters with similar FF fraction, the clusters at slightly lower redshift have a higher level of quiescent galaxy fraction. And to explain this correlation, we suggested so-called web feeding model, and the explanation is like this. So for the clusters, which is connected to the nearby large-scale overdense structures, the fresh galaxies from these structures coming to the cluster, making the quiescent galaxy fraction of this cluster low. So that's our exploration. And we are continuing our study in two different directions. One is we are continuing our spectroscopic observation for the cluster candidates found in the UDS. This one is the another example, which is located at slightly higher.
2
Okay,
minutes left.
okay, thank you. Located at slightly higher redshift of 0.95, and this spectroscopic redshift distribution is showing the redshift distribution of galaxies located within this black rectangular box and observed by Magellan IMAX. And you can see the clear peak at this crystal redshift here. And in this figure, the red symbols are the ones belonging to this redshift peak. So first, we can confirm these cluster using our observation, and then also that there are galaxies located at the same redshift, but outside the clusters, like this. So we suggest that these galaxies are falling to the clusters from nearby structures. And here also these small black symbols are also the galaxies with similar redshift belonging to this upper large scale structure. So we have found another example of the cluster which has a large extent of connected structure and low level of crescent galaxy fraction. And also we are doing in another direction by comparing this trend using the simulation data. I'm using the Horizon on 5. Uh, I believe all of you have seen the movie Hosang showed in the first day, and I'm using that simulation data to analyze the connection between crescent galaxy fraction and large scale structure. So here is one typical example of galaxy clusters, which has very low level of crescent galaxy fraction from the simulation. And we did the similar analysis.
Time's up.
Okay, okay, so yeah, just let me move to the next slide. So we are comparing these two the clusters with the clearly different crescent galaxy fraction and the large scale structures using simulation data. So these two works are still ongoing, and I hope I can show the final results soon. So please stay tuned. And this is my summary. Thank you.
Thank you very much. We got few questions on Slack. The first one is from Matt Markham. So after you get these nice spectra, then you find out that if there is O2 emission, lung emission, that could be coming from some low level of star formation, even though the galaxy is fairly dead. Do you still classify those galaxies as quiescent? That might be misleading, especially if there is a lot of dust settling. Can you comment on that?
Okay, so we classify the galaxies as star-forming or quiescent, not based on the spectroscopic emission or absorption, but on the results of our SED fitting analysis. We use the multiband data from Subaru, Yakult, and IRAC of Spitzer to fit the SEDs of all the galaxies, and then we classify the galaxies as star-forming or passive based on their specific star formation rates. And then we double check the classification by comparing our spectroscopic data, and we were very happy that this kind of galaxies with emission lines are classified as blue or star-forming galaxies from SED fitting as well.
Mm-hmm. Okay, Matt also asked if there is a possible bias, since it is much harder to confirm a galaxy if it has only absorption lines question.
Yes, yes, I agree. So yeah, is it somewhat harder for the galaxies with the observation lines only to confirm compared to the emission lines? Yeah, that's right. So yeah, if you analyze the spectroscopic confirmed galaxies only, that can be biased. For example, the quantity of crescent galaxy fraction, but we included all the candidates as well, applying some weight. You can check how we calculate and apply the weights to the unconfirmed galaxies in our 2015 paper, 2019 paper. Okay, yeah, but yeah, we not only use the spectroscopically confirmed galaxies, but all the galaxies. So we are not much affected by that kind of bias.
All right. Actually, we have more questions, but time is almost up. So I hope that you can keep discussing on Slack.
Okay.
I need to move to the next speaker on for the online people. So thank you very much.
Okay. Thank you.
All right, thank you. Yes. Now the next speaker is also from Seoul National University, John Kim, who will talk about KMNet synoptic survey for of southern skies, KS4. Can you start sharing your screen? Yes, now coming. All right, I can see your screen, so please start.
Okay, thank you. Hello, I'm Junho Kim, PhD student in Seoul National University. This presentation is an introduction about KMTNet Synoptic Survey of Southern Sky, or KS4 in short. The PI of the project is Myung-shi Lim, who is my advisor. We are working with many people in here, and KS4 was started from its need to find optical counterpart of gravitation wave source, actually not related to NEP. But it is an optical sky survey, so I hope it is useful for many other extragalactic studies like presentations in this conference. So I'm starting with motivation of this survey. The gravitational wave detectors detected a signal GW17 or A17, and it is classified as a binary neutron star merger at 40 megaparsec. Within 30 square degree of localization area, astronomers found optical counterpart, which is kilonova, in NGC 4993, about 11 hours after the gravitational wave signal. It was the first optical counterpart of gravitational wave and opened a multi-messenger astronomy era. After the report of kilonova, our research team observed it with KMTNet telescopes 1.2 days after the gravitational wave. For a week of monitoring, we observed a rapidly fading feature of kilonova from 17 to 21 magnitude in I-band. The results are published in 3 papers in here. As I mentioned, we used KMTNet telescopes. This system is composed of 3 1.6 meter telescopes located in Australia, Chile, and South Africa. One other advantage is 4 square degree of large field of view. So therefore, it is very suitable system for time series observation of large area. It has Johnson-Cousins BVRI filter system. For all 3 run of gravitational wave detectors, we made follow-up observation with many telescopes we can use. We call this project as GECKO, Gravitational Wave Electromagnetic Counterpart with Korean Observatory. With KMTNet, we researched optical counterpart of 10 gravitational wave events. However, our team and other astronomical groups cannot find optical counterpart in this run. So all 4 run will start October 2021 with higher sensitivity. It can detect binary neutron star merger at 190 megaparsec in maximum. This kind of event is expected to be detected 10 times with around 33 square degree of localization during the run. With KMTnet, we expect to observe 6 kilonova among the 10 events. We roughly calculated brightest magnitude of kilonova at different distances, assuming the kilonova like GW17 or A17. We can see the light curve in the figure. If the kilonova emit electromagnetic wave at 190 and 330 megaparsec, its maximum apparent magnitude will be about 21 and 22 magnitude in R band. Considering that the kilonova rapidly decreases its brightness about 0.5 magnitude per day and need to be discovered during hours to days, we should take images with 23 magnitude depths at least. When you search the kilonova, host galaxy makes hard to discover the transient. Then we have to subtract images using reference images as in the figure. Here we subtract NGC 4993 with Hanstas image, and we can easily find optical counterpart as in the right figure. So to subtract science image of 23 magnitude depths, we need high quality reference image, which is 23 magnitude depths covering all sky. There are many useful surveys in the southern hemisphere. First of all, our surveys are based on small UGRIZ bands that is different with KMTnet large BVRI system. When you subtract images, it is better to use same band of reference image, but small R band image also work as good replacements for large R bands as previous slide. We can use Pan-STAR survey for declination greater than -30 degree with deep enough depth. SkyMapper covers all of southern hemisphere, but the depth is a little shallower than we need, and seeing is worse than the average seeing of KMTnet. And the DES Dark Survey and VST Atlas and Magnite covers wide area with depths deeper than 23 magnitude, but they still cannot cover thousands square degree in declination lower than -30 degree. Also, LSST will start observation after 2023, but it will cover declination greater than -60 degree in plan. Therefore, we started KMPNet synoptic survey of southern sky to cover the rest area of southern hemisphere. The survey will cover about 7,000 square degree in southern hemisphere, where Pan-STARRS, DES, and VST Atlas do not cover. In the figure, light gray area is coverage of Pan-STARRS, and the dark gray area is DES and VST Atlas coverage, and blue area is KMTNet target area. We appointed the field with low galactic latitude lower than ±10 degree as low priority because it is too crowded area to find transient. Target area will be observed until 2023 using BVRI filters with magnitude 23 magnitude depths and 2 arc second seeing in average. The CCD of KMTNet has a gap in the center as an upper image. So we observe a field with 4 times of dithering and 2 minutes exposure time for each image. Lower image is an example of stacked image. We made pipeline for KS4 project. Basic image reduction such as bias, dark correction, and flat fielding will be done by KMTNet automatic pipeline. We download reduced images and perform astrometry, photometric calibration, bad image removal, and stacking. So the figure shows current observation coverage of KS4 from October 2019. And green fields are observed less than 4 filters or less than 4 times, while orange fields are observed with all 4 bands with our dither. So the survey is finished for orange fields. And total area of orange fields is 190 square degree. And completeness of KS4 is 11% so far. And we measured the seeing full width submaximum of single R-band images taken, okay, 2019 run. The histogram show peaks around 2 arcsecond seeing and 22 magnitude depths. If images are stacked, magnitude depths can reach to 23 magnitude. So although the survey is motivated by searching the electromagnetic counterpart of gravitational wave, we will study other subjects. 2 cases will be studied representatively by our research team. First one is discovery of high redshift quasars together with IR surveys in Southern Hemisphere. Second, lots of galaxy clusters can be found in redshift less than 1 with X-ray and IR surveys. Also, Magellanic Stream, satellite galaxies, stars in our galaxy, and small bodies of solar system can be studied. The public release of KS4 data will be done for astronomical community in about 2 years after observation. It will provide image and catalog as others wide area survey. Detailed plan is not yet decided. So I will stop here and thank you for listening.
Thank you very much. We have a question on Slack from Tomo. How quickly can you respond to the alert, like a gravitational wave, GRB, supernovae? Can you comment on that? This is about the first part of your talk.
Sorry, can you speak?
Yes. Yeah, how quickly can you respond to the alert, like a gravitational alert, GRB alert, or something like that, supernovae?
Okay, we want to observe as quick as possible, but we want to respond within 1 hour.
Great. Okay, we got another question from Albina. It's just commenting that exciting to be able to detect so many galaxy clusters with this surface.
Okay.
Any comments from remote or local participants? I have a quick question. It is about the original purpose of KMTNet, which I think is to have some gravitational lensing survey of by using the LMC or something like that. Can you comment also about that part? Are you still doing this?
Actually, gravitational lensing.
Yeah.
It
Are you
can,
spending 100% time for this survey?
it may be possible, but it's not planned yet. So.
Okay. I see. Thank you. 2 seconds, yes. Okay.
You mean the micro-lensing? Micro-lensing.
So, Oyama-san, what was the question? Was about micro-lensing?
Yeah. Can you
So,
comment on that?
for the KMT-net micro-lensing, so
Yeah.
the micro-lensing is done for the bulge area. So there's a season that the KMT-net can observe that area, right? So which is probably half of the time, and the remaining half of the time, that time is given to other science projects. And micro-lensing survey is ongoing, and I think they are kind of nowadays finding many micro-lensing events. They are being very good at finding exoplanets through that kind of technique now. Yeah.
All right. Thank you for the comment. That is much clearer for me, at least. So thank you very much. So we need to go to the next speaker, which is Yentin Ding.